In a museum vault, there is a sword blade forged in the year 1200, 800 years old. Despite centuries of existence, when properly maintained, that edge geometry remains intact, the steel structure still sound. Now look at a modern kitchen knife purchased 6 months ago. Used regularly, the edge has already rolled. Microchips visible under the same magnification. In another year, it will need professional resharpening or replacement. How is this possible? How can a blade made with primitive tools and inconsistent materials outlast precision-engineered modern steel by decades of active use? The answer is metallurgy, geometry, and a lost understanding of what makes an edge truly durable. Section 1. The medieval advantage was real. To understand why medieval blades maintained their edges so remarkably well, we must first acknowledge what modern steel is optimized for. When someone buys a knife today, they are getting steel designed for initial sharpness and manufacturing efficiency. Modern metallurgy can create an edge so fine it will shave hair straight from the factory. But that perfection is also fragility. Under an electron microscope, the apex of a modern knife edge is a vanishingly thin wedge of metal, often ground to 15 or 20 degrees per side. That geometric precision allows incredible initial cutting performance. It also creates a structure that fails quickly under real-world stress. Medieval smiths could not create edges that thin, even if they wanted to. Their Blumeri-produced steel, full of microscopic slag inclusions and uneven carbon distribution, would not support it. But here is what they discovered through centuries of trial and error: a thicker, more robust edge ground at 30 to 35 degrees with a subtle convex curve actually maintained cutting performance far longer. Modern metallurgical analysis has revealed why. A 2024 study examining medieval sword fragments found that after heat treatment, the cutting edges achieved a Vickers micro-hardness ranging from 500 to 640 HV, with a martensitic microstructure. But critically, this hardness was not uniform. The blade's spine measured significantly softer, creating what researchers described as an optimal balance of hardness and toughness. This was differential hardening, achieved through careful heat treatment. The edge could be hard enough to resist deformation and wear. The body of the blade remained tough enough to absorb the shock of impacts without the entire structure becoming brittle and prone to catastrophic failure. Every time a modern thin-ground edge contacts a hard surface, a cutting board, a bone, even the ceramic of a dinner plate, microscopic damage occurs. The edge rolls over, or tiny fragments chip away. This microchipping is invisible to the naked eye, but devastating to cutting performance. Medieval edges, with more metal supporting the apex, distributed those forces through a larger volume of steel. The edge geometry itself was armor against the abuse of daily use. Remarkably, this insight was not unique to Europe. Halfway across the world, Japanese swordsmiths independently discovered the same principle. By coating a blade's spine with clay before quenching, they created differential cooling rates. The exposed edge plunged directly into water, formed hard martensite. The insulated spine cooled slowly, remaining flexible. The result was structurally identical to European differential hardening, achieved through a completely different method. Two cultures, separated by continents and centuries, arriving at the same fundamental truth: the best blade is not uniform, but composite. But geometry alone does not explain decades of service. The metallurgy itself was fundamentally different. Reading the metal, the lost art of spark testing. Before modern spectroscopy and chemical analysis, medieval smiths had to identify their materials using only their senses. The most crucial skill was spark testing, a technique so sophisticated that industrial metalworkers still use variations of it today. When a smith struck a piece of metal against a grinding wheel, the shower of sparks revealed the steel's composition as clearly as a laboratory report. This was not guesswork. It was empirical science refined over generations. Soft-wrought iron, with almost no carbon, produced long, lazy sparks. They streamed away from the wheel in broad, straw-colored lines about 70 inches long, with almost no forking or bursting. These sparks glowed steadily, but without brilliance. Add carbon, and everything changed. At 0.3% carbon, the spark stream shortened to about 55 inches and began to fork. Small bursts appeared near the ends of the carrier lines like tiny fireworks. At 0.6% carbon, medium carbon steel, the sparks became bushy and bright white, with extensive forking starting close to the wheel. High carbon steel, above 0.8%, produced the most dramatic display. The spark stream was short, only 45 to 50 inches, but incredibly dense. It erupted in a shower of brilliant white starbursts, each carrier line exploding multiple times. The entire pattern began right at the grinding wheel. A skilled smith could distinguish carbon content to within 0.1% by observing spark color, length, volume, and burst pattern. More than that, they could identify other elements. Manganese produced heavily jacketed bursts with brilliant yellow overlays. Nickel suppressed the carbon bursts, creating bright white blocks of light instead. Silicon made the carrier lines end abruptly in white flashes. This was material science conducted through pure observation. No equations, no instruments, just the accumulated knowledge of hundreds of smiths, each learning to read the language of sparks. When sorting steel from a bloom, a smith would test each piece against his wheel. The soft iron went to the body and spine, where toughness mattered. The high carbon pieces, identified by their explosive brilliant bursts, went to the edge, where hardness was essential. Modern metalworkers using spark testing today followed the same principles medieval smiths discovered through patient observation. The physics has not changed. The sparks revealed the same truths they did 8 centuries ago. Section 2. The accidental genius of medieval metallurgy. Medieval steel was not pure. It was not consistent. By every modern standard, it was inferior material. And yet, those very imperfections created advantages we have spent decades trying to recreate. The process began with bog iron oxide deposits scraped from wetlands. This ore was smelted in a bloomery furnace, a simple clay chimney that operated at roughly 1,1200 degrees Celsius. Crucially, this temperature was hot enough to chemically reduce the ore but not hot enough to fully melt the iron. What emerged was a bloom, a spongy mass of iron particles trapped in a matrix of glassy slag. The smith would spend hours hammering this bloom, working it hot, folding and welding it repeatedly. With each heating and hammering cycle, something remarkable happened at the microscopic level. The slag did not completely separate from the iron. Instead, it formed microscopic stringers, like thin glass fibers running through the metal. These slag inclusions created a complex internal structure. When a crack began to form during use, it would encounter one of these slag barriers and be deflected, forced to travel sideways rather than penetrating deep into the blade. But bog iron contained another accidental advantage. The wetland formation process naturally concentrated phosphorus in the ore. When this phosphorus-rich iron slowly oxidized over years of use, it formed a dense, stable film of iron phosphate on the surface. This microscopic coating was non-porous, sealing the metal from moisture and oxygen. The blade resisted not only dulling, but also corrosion, 2 problems that modern steel faces simultaneously. Simultaneously, the repeated heating in a charcoal fire was introducing carbon into the iron, but not evenly. Some areas absorbed more carbon, becoming harder steel. Other areas remained as tough, low-carbon iron. The smith could not control this precisely, but he learned to read the metal through spark testing. The hardest, highest carbon pieces went to the edge. The tougher, low-carbon iron formed the body and spine. These materials were forge-welded together at white heat, creating a composite blade. Not a single material trying to be 2 things, but 2 materials each doing what they did best. This technique of composite construction appeared across medieval Europe. Metalgraphic examination of swords from the period consistently reveals this pattern. A hard edge, often showing martensitic or perlitic microstructures indicating high carbon content and heat treatment, supported by a softer, tougher core. But there was an even more sophisticated material circulating through medieval trade networks. Beyond swords, the tools that built civilizations. While swords capture imagination, medieval edge retention mattered most in tools used every single day: a farmer's scythe blade, a carpenter's plane iron, a woodsman's axe, a butcher's cleaver. These tools faced abuse that would destroy a sword in hours. Consider the medieval axe head. Archaeological evidence from Viking Age and medieval workshops reveals forge welding techniques adapted specifically for this brutal tool. The axe body was shaped from soft wrought iron that could absorb the shock of striking wood thousands of times. Then a wedge of high-carbon steel was inserted into a split at the edge and forge welded in place at precisely 1,000 degrees Celsius. The economic pressure for quality was even stronger than with weapons. A knight might use his sword a dozen times in his life. A carpenter used his tools every day for 30 years. An axe that lost its edge after 6 months meant lost income, failed projects, ruined timber. Museum collections contain plane irons from 15th century English workshops that, when examined under microscopy, reveal 7 distinct layers of alternating hard and soft steel. Each layer was optimized for specific stresses the tool would encounter. The outermost layer, hard enough to hold an edge. The inner layers, progressively softer to absorb vibration and prevent cracking. This was not decorative. This was engineering at an intuitive level we struggle to match with computer modeling. A medieval axe head forged around 1300 could serve 3 generations. Modern reproduction blacksmiths who follow traditional techniques report their axes requiring sharpening far less frequently than factory-made equivalents. One Swedish blacksmith, using period-accurate methods, documented an axe head that maintained working sharpness through 25,000 strikes during timber work before needing attention. The difference was not just skill. It was steel, designed from the beginning to reward maintenance and resist the specific stresses each tool would face. A butcher's cleaver had different steel composition than a woodworker's adze. A scythe blade was tempered differently than a knife. Medieval craftsmen understood something we have forgotten in the age of universal steel grades. There is no one optimal steel. There is only steel optimized for specific work. Section 3. The carbon nanotube secret. 4 minutes. For centuries, a particular type of sword baffled historians. The Ulfbert blades, Viking-age swords bearing the inscription tone VLFB or H+T, were made of steel, so pure and high in carbon that it seemed impossible for the era. The quality would not be matched in European production for another 800 years. The secret was crucible steel, imported from India and the Middle East, where it was known as woots. Unlike the bloomery process, this method involved melting iron ore with carbon-rich materials, including specific plant fibers, in a sealed clay crucible. The result was a homogeneous, high-carbon steel ingot of extraordinary quality. When this steel was forged and slowly cooled, something extraordinary happened at the molecular level. In 2006, researchers at the Technical University of Dresden analyzed a 17th century Damascus saber and made a startling discovery. The blade contained carbon nanotubes. These are molecular structures that material scientists did not discover until the 1990s. Ancient smiths were creating nanotechnology accidentally. The nanotubes formed during the slow cooling process, catalyzed by trace elements in the ore, vanadium, chromium, manganese, cobalt, and nickel. These microscopic structures encased nanowires of cementite, an iron carbide compound that is extremely hard. The result was a composite material at the nanometer scale. The malleability of the carbon nanotubes compensated for the brittleness of the high-carbon cementite. The blade could be incredibly hard, capable of holding an exceptional edge, while remaining flexible enough to absorb impacts without shattering. This explains the legendary properties of Damascus steel. These blades combined hardness levels that should have made them brittle with a toughness that should have required softer steel. The secret was advanced materials science, achieved through careful control of smelting conditions and trace element composition. Modern attempts to recreate true Damascus steel have largely succeeded only by deliberately mimicking these conditions, using steel with specific trace elements, slow cooling cycles, and thermal cycling during forging. If you are realizing how sophisticated medieval metallurgy truly was, hit that like button and subscribe. We are close to 100,000 subscribers, and your support helps us keep uncovering this forgotten knowledge. The chemistry of carbide formation. The carbon nanotubes in Damascus steel were extraordinary, but they were not the only microscopic advantage. Modern analysis has revealed something equally important that explains why certain medieval blades seem to maintain sharpness almost indefinitely. Trace amounts of vanadium, often just 0.005% by weight, acted as a catalyst during the slow cooling process. As the steel solidified, these vanadium atoms bonded with carbon to form extremely hard vanadium carbide particles distributed throughout the matrix. These carbides are significantly harder than the surrounding steel. When the blade is sharpened, they protrude slightly from the edge, like microscopic teeth embedded in the softer matrix. During cutting, the softer steel around them wears away first, but the carbides remain, maintaining the edge's cutting ability even as the overall geometry changes. This created what modern metallurgists call a self-maintaining edge. The blade did not truly sharpen itself, but the carbide structure meant that even as the edge wore through use, it maintained cutting performance far longer than homogeneous steel. Archaeological analysis of medieval blades has found similar carbide formations from other trace elements. Chromium, present naturally in certain iron ores, formed chromium carbides with similar properties. Manganese created its own carbide structures. Each contributed to edge retention in slightly different ways. The medieval smith did not understand carbide chemistry. He simply knew that iron smelted from certain ore deposits held an edge better than others. Ore from Swedish mines was prized across Europe not because of superior smelting technique, but because the geology naturally provided beneficial trace elements. Trade routes developed specifically to move small quantities of high-quality steel between regions. Arabian merchants transported Indian Wootz cakes to Damascus, not just for profit, but because smiths recognized that this particular steel, with its specific trace element composition, produced blades of exceptional quality. This was empirical metallurgy at the highest level. Without microscopes or chemical analysis, medieval smiths identified, valued, and traded materials based purely on performance. They could not explain why Swedish iron made better tools than English iron, but centuries of experience proved it did. Modern analysis has revealed the answer: vanadium content of 0.06% in Swedish ore versus 0.01 to 0.02% in most English deposits. That tiny difference, invisible to any medieval test, resulted in dramatically superior edge retention. Section 4. Why modern blades are designed differently. Modern steel is objectively superior in many ways. We can control carbon content to 3 decimal places. We can add precise amounts of chromium for corrosion resistance, vanadium for wear resistance, molybdenum for toughness. By every measure of purity and consistency, modern steel is better. So why does it dull faster? The answer is economic, not technical. Modern knife steel is optimized for initial sharpness and ease of manufacturing. A factory can grind a blade to a razor edge using automated systems in minutes. That blade will perform exceptionally well in the first weeks of use. Then it will degrade rapidly. This is not a failure. It is a design choice. A knife that dulls in 6 months is a knife that will be replaced in a year. The manufacturing process is so efficient that the replacement is affordable. Different optimization priorities create different results. Medieval economics worked differently. A quality blade might cost a month's wages. That knife or sword was an investment meant to last a lifetime and be passed down. The 7-year apprenticeships, the guild quality standards, the elaborate composite construction techniques, all of this made economic sense only in a system where tools were expected to last decades. Moreover, modern blade geometry is optimized for soft targets. A kitchen knife with a 15-degree edge glides through vegetables and meat with minimal resistance. That same edge would be ruined instantly by the stresses a medieval blade encountered, striking other metal, cutting through bone and sinew, withstanding impacts during heavy work. The convex grind medieval smiths used provided progressive resistance. As the blade cut deeper, more of the edge made contact, distributing force over a larger area. Under a microscope, these edges appear almost crude compared to modern precision grinds. But crude is not the same as inferior. That apparently unsophisticated geometry was the result of centuries of empirical refinement, optimizing for longevity rather than initial performance. The final piece of the puzzle was maintenance. Section 5. The forgotten ritual of edge care. Medieval weapons and tools did not stay sharp without effort. They required constant attention, but the steel rewarded that attention in ways modern steel often does not. A warrior on campaign carried multiple whetstones. After any significant use, He would perform a ritual that varied by blade type and purpose. The process was not random. It was systematized knowledge passed from master to apprentice. For a sword or fighting knife, the progression was standard. First, a coarse stone, around 400 grit, to reshape any damage and remove any rolled portions of the edge. The angle was maintained at 30 degrees per side, measured by feel and muscle memory, 10 passes per side, working from base to tip. Then a medium stone, perhaps 800 to 1000 grit, to refine the edge geometry, 20 passes per side at the same angle, with lighter pressure. The goal was not to remove metal, but to smooth the scratches left by the coarse stone. Finally, a fine stone, 2000 grit or finer, to polish and finish the edge, 30 passes per side with minimal pressure, almost dropping against the stone. The result was an edge that could shave hair, but remained robust enough for combat. But tool sharpening followed different rules, because tools faced different stresses. A carpenter's plane iron required a much finer polish than an axe. The plane iron might receive 50 passes on a 4000 grit stone to achieve a mirror finish, because any scratch marks would transfer to the wood being planed. An axe, conversely, was sharpened to only 1000 grit. The slightly rougher edge bit into wood fibers more aggressively. Over-polishing an axe edge actually reduced cutting performance. Medieval woodsmen knew this through experience long before material science explained why. A scythe blade received the finest polish of any agricultural tool, often to 3000 grit or higher. The blade needed to slice through grass stems cleanly without tearing. A rough edge would bind in the vegetation. Farmers would sharpen scythes in the field multiple times per day during harvest, carrying small whetstones specifically for this purpose. Butchers maintained cleavers differently than boning knives. The cleaver, meant to chop through bone, was ground to 25 degrees per side with only 600 grit polish. Robust and aggressive. The boning knife, needing to navigate between joints, was ground to 20 degrees with 2000 grit polish, finer and more delicate. Here is the critical insight. Medieval steel microstructures responded exceptionally well to this kind of frequent, progressive sharpening. The complex carbide distributions, the slag stringers, the composite layering, all of this created a material that could be repeatedly honed back to sharpness without losing significant metal or degrading the underlying structure. Modern homogeneous steel, particularly the very hard stainless alloys, are more resistant to this kind of maintenance. The extremely fine initial edge is difficult to recreate outside of factory conditions. Many home sharpening attempts actually damage modern blades more than they help, removing too much material or creating uneven bevels. The medieval smith designed his steel to be maintained. The modern factory designed steel to be replaced. Section 6. What this means for you. The legend of medieval blades that never dulled is not entirely false. It is incomplete. These blades maintained their cutting performance for decades because they were optimized for edge retention through every aspect of their construction: geometry, differential hardening, composite structures, carbide formation, and materials that rewarded maintenance. Modern technology has not failed, it has simply optimized for different values. Initial sharpness over longevity, manufacturing efficiency over durability, replacement over repair. For those who want knives that last, the lessons are clear. Look for blades with robust edge geometry, thicker grinds in the 25 to 30 degree range. Seek out steels that respond well to sharpening, often simpler high-carbon steels rather than exotic stainless alloys. Pay attention to trace element composition. Steels with small amounts of vanadium or chromium will hold edges longer than pure high-carbon steel. Most importantly, adopt the medieval mindset. A blade is not maintenance-free. It is a tool that rewards care. Learn the appropriate sharpening progression for each tool's specific purpose. An axe is not sharpened like a knife. A plane iron is not maintained like a cleaver. The real secret of the medieval smith was understanding steel that, when properly made and properly maintained, could serve generations. That knowledge, built through centuries of empirical refinement, represents a sophistication we are only now beginning to fully appreciate through modern material science. The choice we face is not between medieval and modern. It is between tools designed for permanence and tools designed for replacement. Both have their place, but understanding the difference allows us to choose wisely. If this changed how you think about the tools you use, make sure you are subscribed. We are digging up more forgotten technology that challenges what we think we know about the past. And if you want to understand why even something as simple as nails became a luxury that shaped medieval construction, check the video on screen now. Thanks for watching. Thanks for watching.